Welcome back, everyone. Uh, in making up today's lecture, uh, putting together the slides, I realized I probably did not need a third day talking about, or a second day talking about this material, especially not if we're not catching up in tomorrow's catch-up day. So tomorrow I'll probably start off by doing another Tableau or two, another iteration of what we're going to do in just a minute. And then I'll have another Piazza post that you can, if you have any questions, you can post on there. Um, I'm hoping maybe I can go over some of the homework one tomorrow as well, but we'll see. Um, Other than that, I think we're good to go. Yeah, I moved a reading forward to Friday, but we're not going to have a reading quiz on it since we've already had 3 this week. So no need to worry about that. You should do the reading though. Anyway, so yesterday we did the simplex algorithm, which was neat and got us to our optimal solution, but it's kind of cumbersome. There's a lot of moving parts. Yeah. So today we're going to kind of compactify the whole process into a single Gauss-Jordan elimination, or for every new basis that we want to explore. So for every iteration of the simplex algorithm, we're going to do one Gauss-Jordan elimination, one sort of row reduction. So that's neat to compactify all of those different operations into one sort of thing that we should all be familiar with, having gone through linear algebra. So there we go. So the first thing we need to recognize is that matrix multiplication and row operations are actually equivalent things. So remember, there are 3 row operations that we can do in row reduction, Gauss-Jordan elimination. We can take a scalar multiple of a row, we can add one row to another, or we can swap 2 rows. Now I'm going to demonstrate first by swapping 2 rows. I'm going to use this matrix, and I'm going to multiply it by 1, 2, 3, 6, 7, 8, 9. And we take that row times that column, which gives us 4, 5, and then 6. And this row, 1, 2, 3, and then 7, 8, 9, which is the same as the row operation swap row 1 and row 2. That's maybe the easiest one to see, but we're not gonna be swapping rows in today's lecture or in today's material. So let's try taking the scalar multiple of a row instead. I'm going to define this matrix rather. Times our same row. And we see that we get a 2 times 1 is 2, 2 times 2, 4, and 6. Then the rest of the rows remain the same throughout, which is the same as row 1 times 2. And finally, our third row operation was to add one row to another. So we're going to use this matrix. And that is, well, the bottom two rows are going to stay the same, while the top row, we have 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. So this is the same as row 1 plus row 2. So any of our row reduction, row operation sort of techniques can be interchanged with matrix multiplication and vice versa. Correction. Not quite vice versa, because this only works for square matrices. If you're multiplying a matrix by a square matrix, we can replace that with a series of row operations. So remember in our simplex algorithm that we were finding a basic matrix, and then we were finding the inverse of that matrix and multiplying a bunch of things by the inverse. Well, we find the inverse by doing row reduction, just by a series of row operations. So we set up a matrix like this. This side is AB, and then we augment it with an identity matrix. And we're going to perform Gaussian elimination row reduction on the AB matrix. And all of those same row operations will be contributed to the identity matrix. So I'm going to start by saying row 2 plus twice row 1. And we're going to get 1, 2, 0. And also, I'm going to go ahead and divide row 3 by a third. We get a 0 and a 5, 0, 0, 1. And this side becomes 1, 0, 0, 2, 1, 0, 0, 0, 1 third. And then I'm going to row 1 minus 1/5 row 2, and row 2 times 1 over 5. It's going to give us 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have our identity matrix on the left-hand side, and we get this row stays the same. We get a 2/5 1/5, 0. And then 1 minus 2/5 minus not 1/5, but 2/5. 2/5, row 2. So 1 minus twice, or 2/5 of 5 is 4/5. Which is going to give us a 1/5. 0 minus 2/5 is negative 2/5, and a 0 there. And since we have our identity on the left-hand side, we now have the inverse of our original matrix here on the right-hand side. So this this inverse matrix can be re-expressed in terms of row operations. So this is actually row 1 equals 1/5, row 1 minus 2/5, row 2, row 2 equals 2/5, row 1 plus 1/5, row 2, and row 3 is 1/3, row 3. This this inverse matrix expresses all of this in one matrix multiplication. What we're going to do is break up our inverse matrix multiplication into a series of row operations on a slightly bigger matrix. So let's move on to that, to setting that up. Remember, 2 days ago, we talked about the canonical form of a LP at a given basis. So suppose we have the basis B, and we have some LP in standard equality form. This is one of the ways to express the canonical form of that LP in that basis. And notice that we are using our inverse matrix multiplication down here in the constraint section. So we should be able to re-express our transition between these two forms as row operations rather than as matrix multiplications, at least for the constraints. Now the same is true of the objective function, but we need to do a little more reorganizing because it's not quite clear how that new format works out. So what I'm saying is, yeah, we can exchange AB inverse, all of these AB inverses for a series row operations. So let's do a little bit of work on the objective function to get it into a slightly more appropriate format. What I'm going to do is I'm going to write the objective function as an equation rather than as a just an expression, just a linear expression. So remember that this section, that term, is the is over here now. This is the current, or this is the objective function value of the current basic solution. Whereas this term is the improvement offered by increasing our variables. Non-basic variables. And we're going to introduce this new variable, z, which is going to be the objective function value of our LP, of our problem. So, well, of our problem, yes. It just sort of nebulously represents the objective function value at whatever solution we want. So what I've done is I've taken this top term, so it was CB AB inverse times B plus C transpose minus and I've said that for a given solution X, this equation, or this objective function, equals Z. And then I have simply subtracted, excuse me, simply subtracted this term from either side to give us, and then swap the equation around to give us this expression for the objective function. Now I've done this so that we can have one big matrix that will express our objective function and our constraints without having any empty elements. So, yeah. So let's move on to how this actually looks. So let's take our LP, and we're going to just bunch it into one matrix. Now, this is a slightly abstract way of describing a matrix, but we're going to have a section for the new z variable, all of our decision variables and slack variables, and then the right-hand side of all of our equations. So you can see we've taken AX and B, these being A being a matrix, and this 0 being the 0 vector, and this being the vector B, and negative C transpose here, because we have maybe Z minus C transpose X equals C transpose B is our objective in our new Z format. So we have a negative C transpose here, and then we do the same thing for our canonical form. We put it in this matrix. So the canonical form is now of the we do the same sort of operations that we use to get our canonical form of our LP. We do the same idea for our Tableau. So this sort of chart, this big matrix, is called the Tableau, which is French for table, as I understand it. So let's try this out on an example. Let's see how it functions. We're going to use the same example that I did the simplex algorithm on yesterday, but I'm going to do it in Tableau so that we can all see what is going on. Let me get a line tool out. Just to make this a little more legible. We are going to we have 3 constraints. So our Z column looks like this, and our constraint column has the matrix A in it. So 1, 2, 0, negative 2, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. B is 1, 11, 4. The right-hand side of our objective. If you recall, the basic solution with this form, with this canonical form, is the origin, which has a objective value of 0. Then we have 1.5, 1, 0, 0, 0. You could also get this right-hand side here by taking the dot product of these two vectors, because our slack variables are the basic variables at this stage. So how do we read this? This is our x section and our right-hand side section. what does this say? Well, this row that's separated is our objectives, and this is our constraints. But we have one big matrix, and you'll notice that if we take, well, actually, let me write this out. So this is x, y, s1, s2, and s3, specifically those columns. You may see that we have an identity matrix embedded in here. So remember that our basis is S1, S2, S3, and actually I'm going to add our newest variable z to the basis. So it's these 4 columns. A, B for that basis. Is the identity matrix, which means that our basic solution is just AB XB equals B. Our basic solution is just Z equals 0. And well, AB is an identity, so we can get rid of AB from that expression. And we're left with just saying Z equals 0. S1 equals 1. S2, ooh, I'm erasing things. S2 is 11. S3 equals 4. And X and Y were both non-basic, so they are both 0. Which is the same initial starting solution that we had yesterday. So let me copy all this and put it over here. For us, one quick correction. We should have negative c in the objective function row. Negative c. And that changes up our process just a tiny bit. Remember that we wanted that our first step was determining which of our non-basic variables to add into the to the basis. Now, because this is in a canonical form for our current basis, and in fact the Tableau will always, by our sort of operations here, it will always be in canonical form for a given basis after an initialization, which we'll talk about on Friday. So we can identify our non-basic solutions. Well, actually, let me start by saying we can identify our basic variables specifically because they form an identity matrix. So their columns look like an identity matrix. So if we just look at the Tableau without knowing knowing our basis at the outside, we can see that z is in the basis, s1, s2, and s3, they both have, or all four of those have a 1 in one of the entries of that column and zeros everywhere else. And additionally, if we were to scrunch them all together, and we might have to permute them, we might have to change the order, they will form an identity matrix like they did over here. And I wrote a 1 there when I changed this. That should be a 0. So our basis is these guys. And we want to pick a non-basic variable to improve or to change, to add to the basis. So we're going to pick one of these. One of these ones that doesn't have zeros everywhere and a single 1 in the column. Maybe the faster way to identify which variable we want to improve is just to look at the column, or just to look at the objective row. Well, specifically, we want to look at the objective row for the decision variables, because, spoiler, we're never going to change the z column at all. We're never going to take z out of the basis. So we can just look at the decision variable row, section of the objective row, and notice that, hey, if we improve x, that's our smallest coefficient, which means that since this row is actually negative c transpose, that corresponds to the biggest increase in objective function value, because this section is the negative of the objective function. And by our definition of what basis is from Tableau, the basic variables will always have zeros in their objective function entry. Yeah. So we will never pick a basic variable to put into the basis if we just pick the smallest non-zero entry. Or in fact, since we're maximizing, we should pick the smallest negative entry. Because if we picked a positive entry, we would be decreasing the objective function because of this negative sign here. And that's confusing, and that's backwards of what we did yesterday. But it gives us sort of what does it give us? Well, it gives us our right-hand side in a positive format, which is important. So then what? We've picked x. What do we have to do then? Well, in our simplex from yesterday, we said we did some convoluted sort of we did some operations on our linear constraints. And basically what we did was we took b, the b column, bi divided by a xi, x here being the column associated with x. And we wanted to pick wanted to pick the, this is getting a little close to my head, but we wanted to pick the minimum of over I of this for every I in uh, 1 to m being the number of constraints. So in other words, we look at, I'm going to add another column here. This is 1 divided by 1 is 1. 11 divided by 2 is 5.5. And 4 divided by 0 is undefined. So nothing there. And then we're going to pick the smallest one, which for us is 1. And so we're going to pivot on this entry. So what do I mean by pivot? Well, let's get this onto the next page. And we can do that. Paste. So we've picked our pivot. Go ahead and erase all of this extra stuff. We're pivoting on that 1, that entry in the top left of A. Pivoting just means that we want to put A into the basis, or X into the basis, rather. And S1, so this column, we notice that S1 is the basic variable associated with this row. So a pivot is to put one non-basic variable into the basis and take one basic variable out. So remember that a basis cannot have more than m entries, or in this case, since we have our new z variable, m plus 1, m being the number of constraints. So if we put something into the basis, we need to take something out. And we're going to pivot on this entry. So for us, we're putting x into the basis and S1 out of the basis. So we're exchanging x and S1. Now, in the Tableau, today I've said that the basis is the set of columns that forms an identity matrix. This column does not yet form an identity matrix with the rest of the basis. So we want to make this column look like the S1 column because we're swapping out S1. So make the X column look like S1 column. Outside of the Tableau, we did this by taking the inverse of our new AB. You didn't catch the last part. Why did I pick S1? Good question. Good question. That's important. We picked S1 because we took each of the B variables, or the B column, and divided it by the entry, or its corresponding entry in the X column. And then we picked the minimum one. This prevents us from overshooting our feasible region and coming up with a basic solution that would be infeasible. We did the same process yesterday, but it was surrounded by some more algebra and nonsense. So all you need to know for the Tableau is just divide. Once you've picked X, divide each entry of the B column with the corresponding entry of the X column, and then pick the smallest of those entries. This corresponds to how much we can actually increase X by. And in fact, this is going to end up being the value that X takes in our new basis. So now that I've clarified that, all we need to do, well, so again, yesterday, in the sort of matrix algebra format, we took the inverse of AB and then multiplied it by A, and we got our identity matrix sort of implicitly that way. It was a bonus. Here, we want to perform row operations on this tableau to create the identity matrix primarily as our objective, or as our goal. So let me copy this once again. Paste it. I'm going to paste it here, actually. And erase some things. Yeah. So we're going to do some row operations, which means that we're going to erase some of these rows are going to change. Notice that the bottom row is not going to change because there's already a 0 entry there, just like we want there to be. So we're not going to touch row 4 or row 3, depending on how you index things. But we want to put a 0 here and a 0 here. Those are our two goals. So we do that by letting our 0 is going to be our, excuse me, R0 is our objective row. I'm going to index on 0 so that when we talk about row 1, 2, and 3, those correspond to row 1, 2, and 3 of the matrix A. So row 0 is going to equal row 0 plus 1.5 row 1. So I want to cancel out this 1.5 up here. We have a 1. So all I need to do is multiply by 1.5 and add them together to get a 0. And then correspondingly we get 1.5 times 2 is 3. Negative 3, because there's a negative, plus negative 1 is negative 4. 1.5 times 1 is 1 plus 0, or is 1.5. And then these remain in the basis. So these are actually, let me put them in purple so we can see exactly what has not changed. And then row two. Yep, row two. We want to put a 0 there, so that's going to be row 2 minus twice row 1. So we want to cancel out that 2. So we end up with a negative 2 times negative 2 is 4, plus 1 is 5. And 0 minus 2 times 1 is negative 2. Oh, I neglected to change the right-hand side over here. So we'll do that in a second. And finally, 11 minus 2 times 1 is 9. And the top is 0 plus 1.5 times 1 is 1.5. Excuse me, my keyboard decided to lock up. So we have a new Tableau. And just to show you, I'm going to go back to yesterday's notes. And we see that this Tableau corresponds to this this version of the LP that we were solving, this canonical form. Every entry is the same. Of course, we have a negative C in our Tableau, but other than that, everything corresponds. And in fact, we found that we were at 1, 0, which had a z of 1.5, an objective of 1.5, which is, we gotta go back to this page, which is exactly what we have here. Z is 1.5, X is 1, Y is not in the basis, 0, S1 also not in the basis, S2 is 9, and S3 is 4. So instead of remembering all of the different equations and operations that you need to do this algebraically, we've done the same thing with simple row operations. And this is not a coincidence. This is not unique to this problem. This is true for any LP of any size. So this is a pretty powerful tool that will let us do simplex by hand without too much kerfuffle, which is neat. So I'm going to do another iteration or two, and hopefully we can get to the optimal again, like we did yesterday. And hopefully the colors won't get too. Let me. we go. So we're going to look at our objective row, and we see that -4 is the smallest negative value here. In this case, it's the only negative value. So we're going to pick that column. And then we divide B, the B column, by corresponding entries in A, or in the Y column. So we get -1/2, 9/5, which I think was about 1.8, and 4. Now we talked yesterday, we said that this row didn't matter because increasing Y also increased X indefinitely while still remaining feasible. And we can see that because we have a negative here. So we start we pick the column with smallest negative objective function, or C value. And then we pick the row with smallest positive B over A value. And of course, smallest negative means it's the same as largest absolute value. So for this one, we pick this row, which corresponds to S2. So we're going to pivot on this entry, which is happens to be Y in, S2 out. So let's grab our Tableau. Paste it here. And erase the things that are going to change. Actually, let's put them over here again. We have a 5 here. We want to replace that with a 1. So this whole row is going to change. We have a -2. We want to replace that with a 0. So everything there is going to change. We're taking S2 out of the basis, so it's probable that that whole column changes. We'll be adding something here. The right-hand side is going to change. This is a 1. We want it to be a 0. So all of this is going to change. So let's get to it. Row 2 is row 2 times 1/5. 1 negative 2/5, 1/5, 0, 9/5. And then I'm just going to use this row because it's sort of normalized already. It's got a 1 entry there. I'm just going to use that row instead of this row for our next operations, so we don't have a bunch of extra 1/5 floating around. Row 0, oh, I forgot to erase that. Row 0 is now going to be, we had a -4 there, so we want to add for row 2. Which is going to give us a 0. 1/5 plus 8/5 or minus 8/5. We have 3/2 minus 8/5 is, I'm going to peek back at yesterday's notes so I don't have to do that math. It's 0.1. But for us, it's negative. So negative 0.1. And S2 is 0 up here. So 0 plus 4/5 is going to be 4/5. Right-hand side, 1/5 plus 4 times 9/5 was 8.7, if I remember the notes I just looked at. So then the next row, row 1, we just need to add twice row 2 to get a 0. 1 minus 4/5 is going to be 1/5. 0 plus 2/5 is 2/5. 1, so 5 plus twice 9 is 18, is going to be 24/5, I believe. And then finally, a row 3 equals row 3 plus, no, minus row 2. 0, 2/5, negative 1/5. The 0 stays the same. 4, I'm going to peek back. 23/5, so somewhere along the line I missed something there. And 11/5. So our solution then is z is 8.7, x is 23/5, y is 9/5, S1 and S2 are both non-basic, so they are both 0. S3 is 11/5. Which is the same solution we had yesterday. Right. Yeah. Where was it? Where did we write it down? Yeah, right here. Now, I think I have time to do one more, except it's going to be pretty messy because we've got a bunch of fifths floating around. But we can at least set it up. And actually, it will be more time effective if I replace these with blue. So, we still have a negative entry in the objective column. Still only one. So we pick the S1 column and we divide our B column by our S1 column. That's going to be 23. That's going to be negative 18. And that's going to be 22, I believe. Let me check again here. No, not 22. 11/2. Yeah. And you'll notice that this basic, or this canonical form is the same as the Tableau we're currently experimenting with. So this is actually negative 4.5, and this is 5.5. This is our smallest positive, so we're going to pivot on that entry, which means we're going to start by row 3 is row 3 times 5/2. So we get a 1. And 2? No, a 1/2. Negative 1/2. Yep. 5/2 and 5.5 or 11/2. And I'm going to jump ahead. Well, then I'm going to do the objective row. So R0 is 0.1 times R3. That's not quite right. R0 is R0 plus 0.1 R3. Which means we can forget about these. This is 0. And I don't want to do, I think this was 9 3/4. I don't want to do the math, so I'm going to grab it from yesterday's Tableau. We have negatives here, but remember we negate that. So positive 3/4 and positive 1/4. And 9.75. And 1/2 0, negative 1/2. Negative 1/2, 1, 5/2. Oh, no. Yeah. 0 and 0. 1/2, 0, negative 1/2. And then I forgot. Negative 1/2, 1. 7/2, 4. Negative 1/2, 1. 7/2, 4. And those were operations would have been row 1 equals row 1 minus 1/5 row 3, and row 2 equals row 2 plus 2/5 row 3. Now, we only have positive values we have in our objective row. Better yet, we have no negative values in our objective row, which means that there's no non-negative variable or non-basic variable that we can pivot on that will actually increase our objective function value, which means we found an optimal solution. So has no negative entries. So we are optimal. So we're done, and all we have to do is extract our solution. So we have z is 9 3/4. X is 7/2 or 3.5 y is 4, s1, which we just put in the basis, is 11 halves, or 5.5, and s2 and s3 are non-basic, so they're 0. And this is our optimal solution. And that's the same solution that we got yesterday, with, to my mind, a lot less hassle. Does anyone have any questions about this? I will probably end up doing another example tomorrow during a catch-up day, um, just to give us a little more exposure to this process, because this is something that you are going to have to do on a homework. But other than that, now that's all I have. So now we have our method for solving LPs. There's a little bit we're missing. What if our initial canonical form, our initial basis, is not feasible? What if we have that issue? How do we fix that? That's going to be our next step. We're going to do that on Friday, and then on Monday, I believe we're talking about what's called degeneracy, which is the only issue that can sort of come up while doing one of these problems, and we'll talk about what that is. So that's about time. That's all I had to talk about. So I'll stick around for a little bit, but you guys are free to go.